we've gone through sort of 4 wonderful ideas. And namely, conservative line integrals are easy. So if I'm integrating something that's a gradient, well, in other words, it's a conservative function. If I can find f, I just need to know what the value is of f at the endpoints. So f at the endpoint minus f at the start point. Green's theorem, which says suppose I have a region in the plane, I can relate an integral in the region to an integral on the boundary of the region. And then we said, well, you know, Green's theorem works so well, we can move it up into 3 dimensions. And that's Stokes' theorem. So Stokes' theorem says if I have a surface, and I take the curl of f dot n on that surface, which you can interpret as a flux, the flux of the curl, you can find that by looking at the boundary, integral of f dot t. And then finally we said, well, there's Gauss's divergence theorem, which says we can look at a triple integral over the whole space, or the whole solid, of the divergence, and that's equal to the integral f dot n on the surface of your solid. Now, I've chosen to write these in this particular order. Oftentimes we write these in the other direction, but on each one of these I want to sort of highlight what's going on. So you see we're going from a triple integral to a double integral. So over a solid to over a surface. Or maybe we're going from a surface to a curve, a region to a curve. Now you might say, this breaks it, because you're going to a one integral, a single integral, to, there are no integrals here. Well, in some sense you can think of this as a zeroth integral. And so if you think of it as a zero-dimensional integral, then that's what a zero-dimensional integral would be. You just say, take the difference of the 2 points. So these are all variations of the fundamental theorem of calculus. Now, they're both, well, sorry, I shouldn't say both. When I say both, Stokes and Gauss, that's what we're going to focus on today. They're all good to know, but the question is, when do you use which one? So suppose you're out and you spot a problem. You're like, what's the right tool to use? Well, there's a couple of basic rules of thumb. If you see a curve with different starting and ending points, regardless of whether it's a curve in 2 dimensions or in 3 dimensions or in 17 dimensions, doesn't matter. If the curve starts and ends at different points, you should say, I hope this is a conservative line integral. And you look for that tool. Either you look for a potential function, or if it is conservative and you can't find a potential function, look for a better curve. Well, what if it's closed? Well, there's 2 cases. If it's a closed curve in the plane, so in other words, I'm in the xy plane, go to Green's theorem. Now here you have to make sure you pay attention to orientation. All of these things have an orientation built into them. Even this f of b minus f of a has an orientation because it matters what order you take. F of b minus f of a is different than f of a minus f of b. Now if your orientation is ever off, what does that mean? Well, you've lost a minus sign. So if you're a closed curve in the plane, you should be thinking Green's theorem. If you see flux for a region in the plane, that's a variation of Green's theorem. Now the way you compute flux, that's the f dot n. Now this is set up as double integrals and triple integrals. You can also do it as single integrals and double integrals. But flux is related to divergence. Now what if it's not in the plane? What if you're in space? Then the answer is go to Stokes' theorem. So if you see a closed curve in space, you go to Stokes' theorem. If you see something that has the curl involved, you go to Stokes' theorem, because that's a Stokes' theorem type thing. If you see a surface with a boundary, that's Stokes' theorem. So really, Stokes' theorem, what you're looking for is you're looking for some surface with a boundary, or even if you don't have a surface, if you have some curve and you say, okay, I'll fill the surface in. And one of the nice things that we have, I'm going to jump down to this bottom conclusion here, is that you can modify your surface. So if I'm dealing with Stokes' theorem, I can change my surface to fit the boundary. So if you don't like the surface that you're given, change it. In fact, that's probably a good strategy. If you see a surface, you say, boy, if we just had something that was a little bit flatter, I'd be really happy. I have an idea. Make it flat. So keep that in mind. Now, you might say, are we allowed to do that? In fact, it's the same reason that we're allowed to switch our curve when we have a conservative line integral. What matters is what's happening at the boundary. As long as your boundary stays the same, you can change the middle, change how you get to your boundary. All right, what about divergence theorem? What's the key? Look for solid. If you see a solid, you should think, ooh, that's probably divergence theorem. Look for the word flux. If you see, I want to find the flux for a surface of a solid, that's divergence theorem. Or if you have a surface which is closed, in other words, there's no boundary. So you can do things like, for instance, a sphere. I have a sphere, and I want to compute the flux through the sphere. Say, oh, well, that's a closed surface, so I can do divergence theorem. Now, sometimes I'll say, you have a sphere, but you've cut off the top, and now it's a surface with a boundary. Okay, well, that's something else. So look for a closed surface, look for a solid. Those are the keywords. Now, I want to spend the rest of the time just going through and doing a whole bunch of examples. And by doing them, what I mean is to say, let's look at them and say, what's the right tool and where do we go? So before we get started, any questions? All right. So we will not finish these problems, but our goal isn't to finish them. Our goal is to practice recognizing. So let T be the solid given by 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4, and z is greater than or equal to 0. Find f, and here's f. F is 2xz plus e to the y zi plus arctangent xz squared plus y zj plus x minus z squared k. Use the divergence theorem to find the integral of f dot n d sigma. Now, just as a side note, some places you'll see d sigma being used. For instance, your book. That's just a shorthand for notation. What we've been calling DSA. Some people also call it D capital S. It's just different notations. Where G is the surface of T and N is the outward pointing normal vector of the surface. Now, which tool should we use? Yeah, this one's kind of easy. Softball question. It gave it away. But suppose they hadn't told us what to do. What are some other things we can key off of? Solid. Yeah, solid. Anything else? This computation right here says this is a flux through the surface of that. So if you see flux through a surface, that's also another hint. Now, let's not finish it, but let's just make a couple of things. We should practice seeing these things. Do you recognize what this looks like? 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4. Yeah, it's a sphere and a sphere. So if you just look at that, that says I'm outside the sphere of radius 1. And then if you look at that, I'm inside the sphere of radius 4. So I have a sphere inside another sphere. So that's the basic thing. But then there's another constraint which says z is greater than or equal to 0, which means that what our shape looks like is it's a sphere inside another sphere sort of that's been cut in half. So that's roughly our shape. That shape right there. All right. And then what would happen? Well, from here, nothing too surprising. Let's do a little bit more. Sorry. I have a strong tendency. I like to see what happens after this. Divergence of f dv over our solid t. So what is our divergence? What do you get from the first slot, first entry? 2z, because we take derivative with respect to x. From the second entry? Z. Lots of z's here. From the last entry? Minus 2z. 2z and not 2z. Gone. No longer a question. And so, it's just the integral over our solid z dv. Now, we won't finish it, But what would you do next? Spherical coordinate systems. Why spherical coordinates? Because you see spheres. And then this is a beautiful thing in spherical coordinates, right? Everything. Z becomes rho cosine phi, dv, rho sine of phi. All right. Good. Well, that one was pretty easy. All right. Suppose f is minus 2ii plus 2xj plus xy plus z squared k, and S is the surface x squared plus y squared plus z squared equals 9, with z greater than or equal to 0. Find del cross f, it is cross, isn't it? Yeah. Dot n d sigma, where n is the upward pointing unit normal of S. Okay, so what's our surface? What does it look like? It looks like a sphere. Is it the whole sphere? No, because we're cutting it in half. That's the z greater than or equal to 0. So it's a half a sphere. And when we talk about the sphere, we're talking about the shell, that candy coating that you might have if this were an M&M. All right, so it's a half a sphere. So in particular, it's a surface with a boundary. What technique should we use here? Stokes. Yes. What are some clues that we need Stokes' theorem? Surface with boundary. What else? Well, right. This is a fancy way to write the curl. So there's a curl involved. All right. So there's Stokes. Now, one good strategy if you have a Stokes theorem problem is to say, let's think about what we have. We have the surface. We're told that the normals point up, which means if you look in the z component of your normal, it's going to be positive. That's what upward means. The z component is positive. If you don't like your surface, not that we don't like spheres, but spheres can be messy. You get square roots. Make a better surface. The key is you have to keep the same boundary. You can't change your boundary, but you can change the other parts of the surface. So, is there a better surface for us to work with? The disk. So it's like you're taking the sphere and you're deflating it. And so you deflate it down until it becomes flat. And now it's so flat, what's the normal to this? Well, am I going to point up or down? Yeah, I'm going to point up. And in fact, we can actually compute. This makes the normal very easy. And now, when you have a flat thing, it's super easy to finish the Stokes theorem problem. Because really, it's going to become almost like an area. Almost, not always. So what's the next step if we were going to do more? Find the curl. Yeah. When you take del cross f, and if we were in a rush, which we're not, we're just leisurely enjoying calculus. It's a wonderful day in calculus, except I screwed that up. Okay. So now we're in a rush because I messed it up. Because I forgot the second line is the partials, because it is the del. Del comes first. So what would we do? Well, which part do we care about? K. We care about k. Why? Because the other parts are going to go away. So I can say 0, well, not 0, it's something, something, and I'm just going to make a note. These don't matter. Don't matter because of normal. Just so that the grader knows I wasn't being lazy, I was being smart. Sometimes it's hard to tell the difference between the two. All right. And then for the last thing you get k partial x times 2x, which is 2. Then k partial y of minus 2i, which is minus 2. But I have to subtract that. So you end up with something, something 4. And now you take the dot and you're saying, aha, this becomes the integral over your surface of 4 d sigma, which really means it's 4 times the area. Oh, okay, well that's not so bad. 4 times the area. What is the area? Well, what is the disk? How big is this disk? Radius 3. Pi r squared means it's 9 pi, which gives us 36 pi. So that's not so bad. Now, on a side note, these are problems from old final exams. So if you're like, these don't seem so bad. You're correct. We want you to have that attitude going in. These aren't so bad. I'm going to get it.
So,
They can't fool me.
sorry. So with that normal vector, is deflating the surface its only purpose is to find the normal vector?
No, deflating the surface is to make life easier. You don't have to. If you like a challenge, go for it. You'll get an extra page of scratch paper, just in case. So, in fact, every test will come with a bonus page of scratch paper. You won't need it. You're pros by this time. You're seasoned veterans. Just don't make any mistakes. You'll be fine. All right.
Does deflating the region change your bounds?
No.
Okay.
No, it's just you're changing the surface, but you're not changing the bounds of the surface. All right. Let T be the solid given by something. Square root of x squared plus y squared less than or equal to z less than or equal to 2 minus x squared plus y squared. And we have this vector valued function here. Use the divergence theorem to find f dot n. Well, okay. What tool should we use? Yeah. These people, they don't trust you. They don't think you can spot it. But we can spot it. What are some clues? Solid, the flux. We know these things. We see flux on a solid. We're like, that's divergence theorem, even if you hadn't told us. Now, of course, it looks terrible, but it's meant to look terrible because we want only the pure of heart to proceed. We know that really this is going to become a triple integral over our solid. Take the derivatives. What do you get from the first entry? 5 sine squared z. Looks bad, but we keep going. What's the second entry? 5 cosine squared z. What's the last entry? 7. And when we look at that, we say, well, you have to integrate sine squared and cosine squared, but you look at their powers combined. They become 12. So really, this is about integrating and finding the volume of this shape. And at this point, it's like, oh, it's just really finding volume. Well, that's not so bad. On a side note, do you see what the pieces are? Square root of x squared plus y squared less than or equal to z. What is that? It's a cone. Yeah, you should recognize cones. Whenever you see a square root of something squared plus something squared, that's a cone. What about this part? 2 minus x squared plus y squared. What does that look like? It's what? If it was z squared and 2 minus x squared plus y squared to be a sphere, it's not a sphere. It's a paraboloid or bowl. But it's not just any bowl. It's a bowl that's been turned upside down. And, okay, this is no longer to scale, but it's an upside down bowl. Okay, they'll happen to intersect. This, of course, goes down, and this, of course, goes up. But they intersect. And so that's what my shape looks like. It's a cone topped with a certain type of ice cream-like shape here upstairs. Now, at this point, it's all about finding the volume, which we won't continue this on, other than to say, what should we do? What's our next step? In particular, what coordinate system should we be using? Cylindrical. Cylindrical, because this is not a sphere. And there's a basic rule of thumb in spherical coordinates. If you're not a sphere, ugh. Now, it's hard to write that down because the spelling of ugh varies from person to person. But when you don't have spheres, it's a terrible, terrible thing to work with. But cylindrical is great if you ever have something which has rotational symmetry. And this has rotational symmetry. All right. So, here's another problem. Let C be the parametric curve 2 sine t, 0, 2 cosine t, with 0 less than or equal to t less than or equal to 2 pi. It's a circle of radius 2 in the xz plane. And there's the figure there. And, oh, they even showed you the orientation. Well, that's very friendly of them. Find the integral along this curve of e to the x plus 2z, x cubed z squared, log of 1 plus z squared dot t ds. All right. What tool do we use? Stokes theorem. Okay, good. What gives away its Stokes theorem? There's something about this problem that says Stokes theorem is the right tool. What is it? there's a closed curve in space. If you see a closed curve in space, Stokes' theorem applies. Now you might say, but wait a second, there's no surface. Well, that's okay. It's easy to fix. What we have is we have a boundary. We just have to fill it in. And here you can be creative. You can say, oh, I could do all sorts of stuff. Don't be creative. Make it simple. What's the simple surface we can put in? Yeah, put in a flat disk. That's what you should do. Now, here's the part you have to think a little bit about, is suppose you do have a disk. You have the surface. If we're going to switch, the next thing to decide is say, okay, what's the right orientation on the surface? That is to say, I could be pointing in the positive y direction or in the negative y direction. And the reason I say in the y direction, this disk is in the xz plane. To be perpendicular to the xz plane, I'm pointing somewhere in the y direction. All right, so how do I know whether I'm going to go positive y or negative y? Right-hand rule. Yes, if you've had physics, that's good. Or if you have a right hand, which a lot of people do. If you don't remember the right-hand rule, just imagine, suppose I were to stand on this surface. And just pick a side, because it's just a yes-no. So suppose I came and I stood on the surface, and I were to walk along the edge, according to that rule. And I always ask, if I'm walking along the edge, which side is my region on? Is it on my left-hand side or on my right-hand side? Well, if I'm this person walking along the edge, am I on the left or the right? Now, if you're thinking, I can't visualize that, here's a tip. Just turn the paper. And it's like, it's so clear now. I see it. Okay. So, is this the correct orientation or not? Yeah. Yeah, it's the right orientation. Good. Which means there's our n. 0, 0, 1. Now you might say, what if I get that wrong? You lose a point. Maybe 2. It's 0, 1, 0. Yes, sorry. Yes. I'm so used to working in Z. See, I was thrown off because I turned my paper. And if you look at it that way, it is 0, 0, 1. All right. So what do? Well, you give a name to this surface. Don't be creative again. Don't be like, I'll call it Sally. No, S or H or G. And you say, okay, this becomes the integral on my surface H of del cross whatever this part is here. And dot your n, which of course becomes nice, and d surface area. Now at this point you do your cross product. You can save yourself a little bit of work and say, I only really need to pay attention to the y component. It'll probably turn out to be really clean. The other thing to note here is, even if it doesn't come out clean, if this has something where there's a y value, the nice thing is on the surface, the y value for the surface H is 0. So just put in 0 wherever you see y in the output, and that might simplify things even further. All right, well, we go on. Let E be the solid region bounded below by the sphere x squared plus y squared plus z minus 1 squared equals 1, and above by the cone z equals the square root of x squared plus y squared. And S is the boundary of E with outward pointing normal vectors. Find the flux of the field through S. Okay, what's our tool? Divergence. Okay, what are some clues? Okay, we see a solid. We also see what? Flux. And we also have there's nothing for me to circle here, but here our surface is closed because it's the whole boundary. It's a closed surface. Okay, so this is a flux, which merely means we say, okay, we're going to integrate over our solid divergence of f dv, which becomes the integral over our solid, and we do our divergence. In the interest of time, I will try to do it, well, okay, 3 plus 0 plus 0. Oh, it's 3. So it becomes a problem about finding volume. By the way, do you know what this shape looks like? Kind of an interesting shape. Well, let's talk about our pieces. X squared plus y squared plus z minus 1 squared equals 1. What does that look like? It's the sphere. Where is the center at? Yeah, you've moved it up. 0, 0, 1. Radius is 1. So it's a sphere of radius 1. That's been set. Now, we want to be bounded below by this sphere. So it means we want things that are above that sphere. Well, above by a cone. Z equals square root of x squared plus y squared. Well, we've seen this cone so often, we recognize the cone. All right, so we want to be below the cone, above the sphere. You cross your eyes, and what you'll end up getting here is kind of an interesting shape. They intersect up height z equals 1, and then you have your sphere. That's the lower bound. Then you have this cone, which is your upper bound. And so if you were to do a cross-section, what you would see in the cross-section is you would see your circle, which becomes your sphere. Here's height 1. And what it's really found by spinning this around. So that's the shape. That's the shape. Now, if you were going to do this problem, which we're not going to, but if you were going to, what would be a good coordinate system to use? Cylindrical works, and spherical actually works pretty well here. Now you might think, that's a sphere, but it's not in the right place. But it's pretty close. If you look at this sphere, it becomes x squared plus y squared plus z squared minus 2z plus 1 equals 1. The 1's cancel. X squared plus y squared plus z squared becomes rho squared. The minus 2z, move it across, becomes 2 rho cosine phi. So it becomes rho equals 2 cosine phi. So this sphere actually has a fairly nice expression in terms of spherical coordinates. But that's a different problem. We just want to make sure we know how to do Stokes and divergence. Let T be the solid consisting of points x squared plus y squared plus z squared less than or equal to 4 and c greater than or equal to 0. You might get the feeling that we're not good at making shapes. And we're not. There's like 5 shapes we keep using over and over again. So you should know those 5. And the good news is there aren't that many. There's the spheres, cones, cylinders, planes, and occasionally, if we're creative, a box. All right. Let this symbol, which stands for a boundary, so the boundary of the solid has outward pointing normal vector n. Find the integral on the boundary of this crazy expression dot n, dsa. What's our tool? Is this a Stokes problem, or is this a divergence problem? And how do we know? It's a divergence problem. Now, how do we know this is the divergence problem? What gives it away? We see the word solid. What else gives it away? It's a bounding surface. That means it's closed. There's something else. Yeah, this right here, this is a flux through the surface. And so, now you might say, well, wait, doesn't also Stokes have a flux? But Stokes has a del cross. It's a curl involved. If you don't see that curl in that flux, that's divergence. So this is another divergence problem. Let's see, is there anything interesting that happens to this? Of course, you have some very scary looking terms. Y plus 1 to the z. Whoa. But it's not that scary. We can handle it. We can handle it. If you apply divergence, it becomes the integral over the whole solid of the fancy t, which I can't draw very well. It looks like a j, but what? 5x squared. That crazy thing, gone. Here, what do you get in the... Oh, there's a lot of stuff here. 5z squared and e to the y. More crazy stuff that's going to disappear. And the last part, 5y squared and minus e to the y, dv. So the e to the y's cancel. You should, if you see a divergence problem, what you should have left after you do the divergence should be really clean. Like all the messy stuff should disappear. Stuff should cancel, and you're left with beautiful things. This is beautiful. 5x squared plus 5, z squared plus 5y squared. Well, that's 5 times x squared plus y squared plus z squared. Ooh, that's very suggestive. Also, what's our shape? A sphere. Also, very suggestive. So if we were going to finish this problem, how do we do it? Not polar. This is 3-dimensional. So our solid is a half a sphere. So what's the right thing to do for a half a sphere? Yeah, go to spherical. Spherical for the win. Because this becomes 5 rho squared. And then life is good. Life is good. All right. Let's see. Boy, we have had a lot. We need some more curl problems. Is there? All right. All right. We'll pick up a little bit. So suppose you have D as a solid where x squared plus y squared goes between 1 and 4, and 0 is less than or equal to z less than or equal to 2. So it's a cylinder with a smaller cylinder drilled out. Very conveniently, they gave us the picture. Let S be the surface of D, and N be the outward pointing normal to D. Then we want to find the following. Integral of y to the fourth minus x to the fourth of 4x cubed plus y plus r, blah, 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 dot n d sigma. Okay. What's the right tool? Divergence. How do we know that? Yeah, we see solid. We see a flux happening here. Now, here's a question though. Look at your surface. That's a holy surface. It has a hole. Are you allowed to do divergence theorem if you have a hole? Yes. Good. Well, that was easy. All right. Look, it's okay that there's a hole. No problem. So one of the things, of course, is, when we talk about outward normal, it depends. So you can, on parts of it's pretty easy, but, outward normal here, we're actually pointing sort of towards the inside. It just depends where your surface is. But holes are perfectly fine. Don't worry about holes. The theorem still works. And essentially, if you're worried about, well, why does it work? Just cut it so there are no holes. The same thing that we did in Green's theorem. And then it works out. So here, you can probably guess where you're going to end up going. What's the right coordinate system to use? Cylindrical. Yeah, it's dead giveaway. Cylinder. All right. Let D be a solid with x, y, z greater than or equal to 0, y less than or equal to 1, x plus z less than or equal to 1, z less than or equal to 1 minus y squared. That's the picture. Now notice, that is not a sphere, it's not a cylinder, it's not a cone. It's like something you wouldn't want to step on. That's what it is. Now you might say, whoa, are you saying that we're allowed to do these problems on shapes that aren't round? Yes. We oftentimes go to cylindrical and spherical, not because that's where the theorem works, but just because those are the fun ones to do. These ones tend to be longer because you have to set stuff up. But we don't mind setting stuff up. We're getting good at that. And okay, so S is the surface of this solid. Find the following. We have this crazy expression, dot n d sigma. Simplify as much as possible. Now, what's the right tool? What's our tool? Divergence. Yes. How do we know? We see solid, we see flux. We think divergence. Now, in this case, this one takes some work. So we're definitely not going to do it. But it's fun to work this one out. You get 7. All right. So suppose you have F, and C is the intersection of the cylinder, x squared plus y squared equals 1, and the plane, x plus z equals 1. So you have this surface here. Now what does it look like? X squared plus y squared equals 1 is a cylinder. Now you might say, how do you know it's a cylinder? Because it says it right there. That was my first clue. All right. So I have this cylinder here, x squared plus y squared equals 1. And that's sitting here in my x, y, z space. Now I have a plane, x plus z equals 1. Now what does that look like? Well, in the xz plane, x plus z equals 1 looks like a line. So when I go to 3 dimensions, what does x plus z equal 1 look like? Well, it looks like a plane. And so I have this plane coming through, slicing the cylinder, and so the result of this slice is sort of kind of an ellipse. So there you go. There's your curve. There's your C. Now, that's the intersection of the plane with the cylinder. It's oriented, and it's oriented in such a way that if you were to look straight down the z-axis, so from above, it's going to be oriented counterclockwise, which means that we need to think about what counterclockwise means. No, that's not so bad. That's counterclockwise. All right, so now we have an oriented curve, and we want to compute the integral along this curve of f dot t ds. What do we do? Well, what's the right tool? This is a Stokes theorem tool. Now, how do we know it's Stokes theorem? Well, it's a curve in space, so that's a clue. There's no solid. You might say, well, wait a second, isn't the cylinder a solid? The cylinder, notice it's an equals one. I'm the shell of the cylinder, so it's the shell of the cylinder intersect the plane. Okay, so it's a curve. Another thing is just count how many integrals there are. There's one integral sign, which means this is a one-dimensional integral. Divergence theorem is out. Divergence theorem says I can swap between a three-dimensional and a two-dimensional. So there's no way this can be a divergence theorem. Okay, so you have a curve in space, and you want to compute this. Now, how do you actually compute this? What's the right thing to do? At this point, there's a couple of choices. One choice is actually do this. It probably isn't terrible. I'm probably guessing some power reduction. But you can just say, you know what, I don't have to use any of the tools. I'll just brute force work my way through it. But odds are pretty good if they're asking you, there's a more elegant way. So what do we do? What are we missing here if we're thinking Stokes? A surface. So we got to put a surface here. Well, what surface do we put in? Probably we'll put in the flat thing. Now, when we say the flat thing, what is the flat thing? And the flat thing is, this is the x plus z equals 1. That's the flat part. So it's the x plus z equals 1. Now, here, we can do the following. We can say the integral along the curve of f dot t ds is equal to the integral on our surface, call it S for now, of the curl of f dot n dsa. Now, because of the orientation, will my normal vector point upwards or will it point downwards? It's an upward pointing normal. Because if I were to stand on this and walk around, I'd say, aha, I'm standing on the right side. The top side is up. So the normals are going to point. They're not pointing straight up because this is not z. This is not a z equals something surface. It's x plus z. So it's a tilted surface. But at least it has upward pointing normals. Now, del cross f, well, we can't, we've got to face the music, got to do this one. All right, so here's f. So we have I, j, k, partial x, partial y, partial z, x squared minus 2xy, yz. So what are we going to get? I partial y of yz, that's z. J partial z of x squared, that's the I, 0j. K partial x of minus 2xy, that's minus 2y. K, so going down. Now go the other way. I partial z of minus 2xy, nothing there. 0i, subtracted. J partial x of yz, nothing there. That's great. K partial y of x squared, nothing there. So we end up with z0 minus 2y. So that's curl. So what do we have? So this is the integral of our surface of z0 minus 2y dot n dsa. Now, how do you actually compute that? Well, you do it in the following way. We remember that the integral of a surface in general of mnp dot n, whoops, I'll put s here, dot n dsa is equal to the integral over the region in the xy plane of minus m fx minus n fy plus p dA. So we computed to an integral here in the plane. So if we do that, this will be the integral over our region in the plane. M is, well, what's our surface? It's here. So our surface is z equals 1 minus x. So we're going to get minus m, which is z, times f sub x, which is minus 1, minus n, which is 0, times f sub y, which is 0, plus p, which is minus 2y dA. But z we can replace by 1 minus x. So minus, wow, there's a lot of minuses here. This is getting really messy. But it's all there. So you get 1 minus x minus 2y. And that's the integral over your region R. What's your region R? Well, it's the region that you'd see if you look straight down the z-axis. And what region do you see? The unit circle. Okay, so what's this integral turn out to be? Yeah, it turns out to be pi. Now, you're probably thinking, you did that a little bit fast. Can you slow it down? Yes. What does this turn out to be? No, that's not what we mean by slow it down. Okay. Minus x, there's symmetry. You can flip left, right. And so you get cancellation. Minus 2y, symmetry, you can flip up, down. So when you integrate the minus x, that'll go away. When you integrate the minus 2y, that'll go away. You're left with the integral of 1, which integrates 1, finds area, and the area of a circle is pi. So all that work for a pi. Well, must be good pi. Okay. Consider the open trough formed by taking the surface of the solid, formed, wow, there's a lot of forming here going on, but we have this cylinder, x squared plus z squared less than or equal to 4. So that's a cylinder. If we think of our picture, and here we have the x, y, z, x squared plus z squared less than or equal to 4, you start with the circle in the x, z, and you move. So that's x squared plus z squared less than or equal to 4. It's this sort of solid cylinder. But we're just taking the surface of that solid. So now, just the outside. And then, we're going to go further. We're going to say y only goes between 0 and 3. So we're going to cut off the ends. And finally, z is less than or equal to 0, which means that this was a very complicated way of saying we have like a trough. That looks something like this. So this is a solid trough. So there's ends here and there's stuff on the side. All right. So it's our trough. So that's our surface. Now, good. Whew. Find the integral on, what is this? This is really supposed to say the boundary of G. Okay. Find the integral on the boundary of G of x, y minus z plus x dot TDS, where the boundary is oriented counterclockwise when viewed from above. All right. What's the right tool here? Other than being confusing, what do? This is Stokes. Because, what do we see? A surface with a boundary. So the boundary is a rectangle in the xy plane. Now, probably our surface is not the right surface. What's a better surface? Just a flat rectangle. Just push it up. And now we say aha. Do we say aha? Yeah, we say aha. It's oriented counterclockwise when viewed from above. So this is still oriented counterclockwise. when viewed from above. And we're ready to go. So make it flat, go from there, life is good. All right, I think there's one more. Let G be the surface consisting of the two parts. So one part is you have R equals 1 for 0 less than or equal to Z less than or equal to 2. So it's a cylinder. And then x squared plus y squared plus is less than or equal to 1 for Z equals 0. So you have the bottom here, and then you have the sides. So that's our surface. There's no top. It's like a drinking glass set on the xy plane. Now let n consist of the normal vectors which would point out. So in other words, n is doing this. Downstairs it's pointing down. Okay. Determine the integral on this surface G of curl of something dot n dsa. Well, what problem is this? What kind of problem? Stokes problem. What gives away that it's Stokes? The curl. You see a curl, it's a Stokes problem. All right. So we're doing a Stokes problem. Now we have two choices. Well, we have three choices. Actually do this. That's the wrong choice. So we're not going to do it. Or we could say, let's switch to the boundary, figure out what that is. But there's probably a better way. What's our better way? Change your surface. Now, what do you have to keep? You have to keep the boundary. The boundary is just that top rim of the glass. So what's the better surface? The disk. Just make it flat. Which way do our normals point? They're going to point down still. You have to be consistent. And now, once you've done that, it's pretty easy. Nothing surprising. And that was it.